Uh, so today our topic is the support vector machines, or it is familiar as SVM, support vector machine, or SVM. Okay. So now, before discussing this, let us go to the classification problem. So we know that in the classification problem, there are some data, there are some positive data like this, and some negative data like this. So these are the plots. Now the thing is that by applying nearest neighbor algorithm, we can divide this into two groups, the positive groups and the negative groups. Similarly, by applying ID3, we can divide these classes as like this. Okay, by applying neural networks, we can divide as this. So somehow by applying the classification algorithms, we can divide this data into two classes. One is positive classes and there is negative classes. Okay. So somehow what we will do, we will design or draw a line here to differentiate this plus and this minus data. Now the question is that, say we can draw a line like this which is touching the negative or maybe very closer to negative. We can draw a line which is very near to the positive. We can draw a line like this, we can draw a line like this. So the problem is that, yes, the classification line is, or maybe we have infinite number of such lines. Okay, now the thing is that which one to choose. Okay, so for this, actually the mathematician Vladimir Vapnik introduced this SVM in 1995. So this is a long history that how Vapnik got this. Actually he got this during his PhD studies, but after that, for the Cold War between Russia and America, so he has not published any paper that time. But after few struggles, after his three papers have been rejected in an international renowned conference, and sometimes he was talking with his colleague, and he was discussing with his ideas, and after that he implemented his algorithm, which he did during his PhD on statistics, and he got the success, and after that SVM have been accepted by the machine learning people. Okay, those who are working with machine learning. So now the thing is that problem is, okay, that we are having some positive records, we are having some negative records, and we have to find a line. And again, I am repeating, the question is that there are an infinite number of lines, and the question is that which one to choose. Okay, right. So we'll solve the problem here. Now, so first our target will be to find a road like this which is touching these 2 points for the example. Okay, so these are parallel obviously, and we are considering the median as this. Okay, now think about, if we can maximize this one, the depth of this street, then what we can say, any data on this side of the road must be positive, any data on this side of the road must be negative. Okay, so if we can maximize this depth somehow, then there is a chance to classify the positive and negative records. Okay, So our target is to maximize the depth of this street. This is known as the street, or sometimes it is known as a gutter also, gutter trough. Okay, right. So before going to that, what will happen? So first we will think about that. Let W is a vector which is perpendicular to the mean of this street. Okay, W is a normal to the mean of this street. So let this is the street. Okay, so if we think about this, any data, let any data, unknown data u bar, which is here, if we find this vector here, how to classify that, whether it belongs to a negative class or belongs to a positive class, right? So the thing is that if we project this data on this W, so that means projection means W bar dot U bar, and if it is greater than some value, let's see, okay, W bar dot U bar, that means this unknown data has been projected on the normal and we are finding this dot product, and if this value is greater equals to C, then we will say that this W is positive class. If not, then it is negative class. Okay, so in other way, what we can say, that W this plus this one is greater equals to 0. W bar dot U bar, that is these two vector, the vector product of this plus B is greater equals to 0, right? So here from this we can say that this unknown data is in positive class if this condition is true. So we can say that this is condition number 1 or equation number 1, right? So from here we can say that if any data belongs or is on the street, then this value W plus B is equals to 0. If it is greater than 0, then it is the positive side. It is negative, then it is in the this region. Okay, so therefore we can say that this is positive for positive values, and W U plus B is less equals to 0 for negative classes. Clear? Right. So then what we will do? So all points here will be W dot U plus B equals to 0. So that means it is within the gutter or the street. Now let us consider one variable or output variable y suffix I is equals to plus 1 if the data is positive plus, y suffix I is minus 1 if this is negative plus. Okay, so now what we found, first we have got that this is Wx plus B equals to 0, this one is Wx plus B equals to 0, this one is Wx plus B, we can say that this is plus 1 and we can say that this value is minus 1. Okay, so here we can write Wx plus B is greater equals to 1, or this is plus 1, this one is Wx plus B is equals to minus 1, and this is Wx plus B equals to 0. We can consider these three straight lines. Here 1 does not mean 1 centimeter or something, this is 1 unit, later will come. Now think about this. If the condition is that if it is a positive class, then W U plus B greater equals to 0. If it is negative class, then W U plus B less equals to 0. We have considered one output variables y, which is plus 1 if positive, y minus 1 if negative. Now can we write this as W sorry, yi w bar xi plus b is greater equals to 1 for any data x. Let us consider for any data xi. Okay, this is a vector. You can write this also, or xi. So this is for positive class. Similarly, can we write this yi w xi plus b is also greater equals to 1 for negative classes also. Why? See, if we consider that this is wx plus b greater equals to 1 for positive classes, wx plus b for negative classes. Now, if a data belongs to here, that is yi is also positive plus 1. Here, if a negative class here, then yi is minus 1. So if we multiply minus 1 with minus 1, it will be plus 1. If we multiply plus 1 with plus 1, it will also be plus 1. Therefore, here we can write that yi this is greater equals to 1 for positive class, yi into this greater equals to 1 for negative class also. Therefore, what we can write? We can write for any data, this condition will be true, greater equals to 1. Or in other ways, we can write yi wx plus b minus 1 is equals to or greater equals to 0. Okay, so for the initial conditions, that means if it is equals to 0 and right side of this, immediately we can say that this classification is done. So the condition we have to check is yi w x plus b minus 1, whether this is 0 or not. Okay, so that one we can write case 2 or equation number 2. Okay, right. Now, so first what we have got? We have got if it is positive, then it will be this one w or wx plus b greater equals to 0, and the condition is that it must be also true, yi wx plus b minus 1 must be greater equals to 0. Okay, now think about a situation like this. Here, say we are having a positive data here and a negative data here. What will be the distance between these two? That this is x plus positive value, here x negative value. What will be the difference between these two, the data? If we make a projection towards w, okay, since this is the normal, so if we make a projection towards w like this, and if we project this value here, so then what we will get? X plus minus x minus, right, multiplied by w. Got it? So therefore, if we have a positive data, let x plus and a negative data x minus, then what will be the difference between these two? The difference between these two will be x plus minus x minus, okay, multiplied by w and the norm w. This is the unit vector. W by norm w is the unit vector, and the difference between a positive data and a negative data will be the dot product of these two. Then we can get this one. Okay, now think about this value. What will be this one? If we multiply w x, okay, when yi is positive here, when yi is positive, wxi wxi is equals to 1 minus b, because y is plus 1 or positive, whatever we have said. So here we can say that wx is 1 minus b from this equation. Okay, similarly, whenever we have yi is negative, then what we will get? Minus yi wxi minus b minus 1. So we will get minus wx is equals to 1 plus b in the other side. Okay, so therefore here we can write wx is 1 plus b, and if we take this one, what we will get? 2. Therefore this value will be equals to 2 by norm w. So the distance between a positive class and a negative class is equals to 2 by norm of w, right? So here we have two variables to found. If we can find the w in this equations, wx plus b in this equations, these two are unknown to us. If we can find this vector and this constant b, immediately we can find that whether it is greater or equals to 0 or not. If it is greater or equals to 0 or plus 1 anything, then we can say that it is positive class. If it is less than minus 1, it will be negative class. So our target is to find this w and this b, and the distance between a positive class and a negative class is 2 by norm w. Okay, therefore what we have told? We have told that our task is to maximize this distance or the depth. Now we have found that this depth is this 2 by norm w. Therefore our target is now, or the problem is now, we can write the target is to maximize 2 by norm w. In other ways, what we can write? To minimize this. Okay, for mathematical convention, what we can write? To minimize half this, which are same. If the problem is to minimize this, it will be equivalent to minimize half of this, because this value is positive and we can apply any functions of this one. Okay, right. So the target is now to minimize half of this one. Now you can ask the questions, is it only for mathematical convention that we are choosing these values? No. This w is a linear function. Now if we apply, so it may have more than one optimum value. So whenever we have applied the square here or parabolic functions, so therefore we can expect that there is only one global minima or global optima. Okay, so this is another reason, and half is added to later you can find that whenever we will go for finding the differentiation, it will be cancelled, nothing else. Okay, so for mathematical conventions, without finding the minimum value of mod or the norm of w, we are finding half of norm of this square. Okay, right. So therefore our problem can be formulated as to minimize half of this subject to, we are having a constant. Later we have here we have shown the constant is as yi wx plus b minus 1 equals to 0. This is a constant. So you have to achieve this, and after that, if it is greater than, then it is positive, less than, it is negative. Okay, so the condition is this: for both positive and negative, we have to qualify this equation, right? So our target is to minimize this value subject to y suffix I, w vector xi any data plus b minus 1 equals to 0. Now we know that whenever we have to optimize a function fx, right, with a given constraints gx equals to 0, we can rewrite this equation by applying Lagrange. Okay, so the Lagrange is providing as to optimize Lagrange of xa, which is equals to fx minus a constant a into g of x, and the determinant of xa is equals to 0. Okay, where this a is known as Lagrange multiplier. Okay, right. So here, to find the optimum value of this half of norm square, we will apply the Lagrange equations. Okay, so in that case our Lagrange equations will be like this. We have to find the minimum let L is equals to half of norm square, that is fx, minus later I am writing y, sum of, let the Lagrange multiplier is denoted as lambda I. What is gx? Gx is y suffix I w bar xi plus b minus 1. Okay, so here, since we are having m number of data, I equals to 1 to m, since we are having m number of data, we are applying this minimizations for m number of data, therefore we have taken sum of all these. Okay, right. So with respect to w and b, so you have to find the minimum value of L, where L equals to half of norm square minus I equals to 1 to m lambda I, where lambda is the Lagrange multiplier multiplied with the gx yi w xi plus b minus 1. So we have to find this value here. Okay, so that we can write as this: half of norm square minus lambda I yi w xi plus b plus lambda I, sum. So here all are I equals to 1 to m, I equals to 1 to m. So if I miss this, please consider that all the sum is I equals to 1 to m till I do not mention. Okay, right. So next, what to do? From the property of the derivative, we know that the first derivative must be equals to 0. To find any optimum value, the first derivative must be equals to 0. So here we can write the delta L by delta W is 0. That implies, here you see the equation that we have wrote is equals to half of norm square minus this and this. So if we go for finding, just check here the derivative with respect to W, what we will get? If we find the derivative with respect to W, we will get that it is equals to half of this. So 2 will be discarded here and w. Now see, this norm is providing us the value, but whenever it will be w, so it will be treated as a vector only. Okay, then it will not be the norm. Clear? Right. So actually this comes as w into w transpose. So whenever you are discarding one, only one w will be there. So then w is a vector only. This is not the value. Please mind that. So from here we can write delta L by delta W is equals to W minus, here what we will get, W is the variable, so therefore it will be lambda I yi xi, right? So minus lambda I yi xi, this b is a constant. Clear? So lambda I yi b with respect to w, the derivative will be equals to 0, and this is also 0. Clear? So therefore we can write this value is equals to 0. So we can write that this is equation number 3. Okay, right. Then if we take the derivative of delta L with respect to delta B, with respect to B, what we find? Here again you check this value with respect to, if we take the derivative with respect to B, this is 0. This one is also 0. This is 0. Only one thing we will get, that lambda I and yi. Okay, the sum of lambda I yi. So we can write that, obviously it will be minus, but we can say that this value is lambda I yi, which is equals to 0. So minus this is again also 0. Clear? So this is equation number 4. So from equation 3 and equation 4 we can write that w is equals to lambda I yi xi, and this value lambda I yi is equals to 0. So we have got these two. Okay, right. After that what we will do, let us substitute these two values in the equation here. Okay, in this equations. So here we have got w, here also b. So if we place this value w from here, whatever we have got, and b this from here, whatever we have got, then we can replace all these values and we may get the value of minimum L. Okay, so then what we will get, the minimum L is equals to half. See here again, w norm w square means w into w transpose. So actually we are multiplying two vectors, nothing else. So two vectors means, here two vectors means one is ith data, another is jth data. So two different vectors means ith value and the jth data. Okay, so therefore we can write this norm square is as, one value is say lambda I yi xi, and another is lambda lambda j yj and xj. So if we take the dot product of these two, then we can say that this is the norm square. Okay, similarly minus, here minus, we will replace this value, substitute the value of w and this value b. Okay, right. So what you can say here, minus lambda I yi lambda I yi, then here we will replace this value by lambda, this value by lambda j yj from here. See here, this w we are replacing lambda j yj xj. Why? Because already we are having here lambda I yi. Here we are having the lambda I yi and xi. Therefore here w will replace by lambda j yj and xj. Okay, so we can write like this. Let us write lambda I yi xi multiplied by lambda j yj and xj w minus lambda I yi b. Okay, so minus lambda I yi b plus lambda I yi b plus sum of lambda I. Got it? So here we can give this value as the double multiplier, because we are having two different data I and j, and here like this. Similarly, we can just replace this value as half of double summation lambda I lambda j yi yj xi dot xj, like this. So you can remove this value also, minus double summation lambda I lambda j yi yj xi xj. You can multiply this or write like this, anything. Okay, now what is this value? Lambda I yi 0 already have got from here, so we can replace this value. It will be 0 and plus lambda I. Okay, so we can write that this equals to lambda I minus, here from here we can write half of this minus half of sum of lambda I lambda j yi yj xi xj. Okay, all values are I equals to 1 to m, I equals to or j equals to 1 to m. Clear? So now see, from here what we have got, minimum L is equals to lambda sum of lambda I, which is constant. So the Lagrange constants are known to us. These two are Lagrange's constant known to us. Yi, yj, the positive and negative values, the variables that we have considered. Now the question is that xi and xj. So we can, if we can find the multiplication of xi and xj, that is two data, immediately we can find the minimum value of L. So previously it was looking like that, how to find this w, how to minimize the w and all these things is simply if we can find this sum equations, then immediately we can find the minimum value of L. Okay, right. So what we require, the thing is that all we have to find the dot product of xi and xj, nothing else. So if we can find the dot product of xi xj, if we know if the Lagranges are known, Lagrange's multiplier are known to us, immediately we can find this value. Okay, so therefore from here again, from this equation lambda I yi equals to 0, if y is given, if this vector is given, then immediately we can find the lambda I. So the Lagrange multiplier can be also found from these equations, which can be placed here to find the minimum value of L. Okay, now the thing is that if a new data comes, after knowing this lambda, if a new data comes, then we have to, or we can get the margin, the maximal margin separating hyperplane as w equals to simply lambda I, yi, xi. Okay, so if we can find this value, immediately we can get the classifier. Okay, and after, so from the training data we can find all these w, lambda, y and all these values. So after training and finding the w, what we can go, if we have given a new data u, then immediately we can classify this u as fx is equals to w into u. Previously we have wrote this plus b. So how to find this value? We know this w is equals to this. So lambda I, yi, xi, it will be multiplied with the new data u plus b. The value b is known to us. And from here, if we get this value as positive, it will be the positive class. If it is negative, it will be negative class. Okay, so in this way we can apply SVM, the support vector machines, to classify for linear data. Okay, right. Now the thing is that the question is that if it is non-linear, if the records or the data are non-linear, then is it possible to apply the SVM to classify? Let us consider this kind of situations. Let we are having some data like this. Say these are positive values. Okay, let these are positive values and these are some negative values. Now is it possible to apply the SVM here? Yes. So we can apply some tricks which are known as kernel tricks. We can apply some kernel tricks to convert this nonlinear data into linear. How? See, here all these x values are given. Okay, all the x values are given. If we apply a technique where we can do that, suppose we are having a three-dimensional data, okay, and this is let the plane, and above the plane all are positive and below the plane these values are negative. Okay, so if we can apply these tricks, then immediately we can find two separate space to this. Okay, similarly, let we are having some records like this. Say these are some plus records, these are some minus values, and again some positive records are there. How to apply SVM here? Again the problem. So there we can do a trick. Suppose these values are x. Okay, we are converting by applying a kernel in this process. Let x square. Okay, so immediately if we apply this kernel tricks, this value, these linear values will becomes this one. So let these are all positive, then these are negative, then again these are positive parabola. So if we can apply this here, we can get linear, and if I can apply, you can find this line here, so immediately we can apply the SVM. So here you see, sorry. So after applying this kernel, this one. So there are different kinds of kernel tricks. Okay, so we can apply all these to convert a non-separable data to a separable one. Okay, so this is all about SVM. Thanks.